Okay.
How's it going, everybody? My name is Patrick Aarons,
I'm Julie Perfetto.
and today we're going to do Chapter 53 of Winston, focusing on the traveling salesperson problem.
So the traveling salesperson problem is an interesting topic and has been studied for a while because it presents a lot of different cost-saving opportunities if companies are able to minimize the distance that their salespeople, or in this case study, UPS, the distance that they travel. So for UPS in particular, they found that if each UPS driver drove just one less mile per year to deliver their packages, they would save $50 million. So this is the classic traveling salesperson problem. Suppose you're given a starting city and a list of cities to visit. You know the distance between each pair of cities, and you need to visit each one just once and return to the starting point. What you're trying to figure out is what sequence of visiting these cities requires the smallest distance. So how can we solve for this problem? It's difficult because of the number of possible solutions, or tours as we refer to them. If you had an example with just 30 cities, there are actually 442 followed by 28 zeros possible tours. We notate it in scientific notation, 4.42 times 10 to the 30th power. So obviously with this many different possibilities, we need some sort of resource to solve. So in this instance, we'll utilize Microsoft Excel. And UPS in particular has quite a few complexities with their traveling salesperson problem. They can't just use a straightforward approach of finding just the shortest distances. They have contracts, and some packages have to be delivered by 10:30 a.m. So they have to modify the traveling salesperson problem to penalize tours that wouldn't deliver those packages on time. They also have to build in lunch and break times, and drivers in certain parts of the country could be on the border of two different time zones. And then they also might have certain routes that they don't want to use on their route, like maybe the roads are unsafe, or there's a lot of traffic. There's, different things to consider. And in spite of these challenges, they think that the Orion software is what UPS uses to determine these routes. And they said that one driver saw his daily travel distance decrease from 150 miles to 126 miles. So overall, it seems like there's quite a bit of satisfaction, even though there are challenges for UPS.
Yeah, so the other big part about this TSP problem and the chapter itself was focusing on the TSP problem in Excel and its kind of its relation to us in class. So pretty much what they did was they started out with the city, order, and distance as the first three columns. From there, we then added the distance matrix down the path, looking here from like F to, I believe it was A1. With that being said, we also allocated a number 1 through 30, odd and even, to each city, Orlando through Miami. We then used for the first column B2 or C2, I'm sorry, we used the formula E equals index with distances being the matrix as I referenced before from F to A1, AI 131, B31 to B2 because it was the different distance between the first city to the last city. We then got the overall distance from first to last. From there, we then used the index equals index formula distances B2 to B3 from Atlanta to Memphis, kind of just saying that so we get the total from Atlanta to Memphis. We then copy that formula all the way down to B31 or C31, I'm sorry. So then we get the distance from each city to one another. We then in C32 use the equal sum formula to get the sum of the total distance of every single one of the distances from each city to another. From there, we then go to the data tab and use the Excel solver. And then we do the solver parameters. Now the solver parameters in this case are the objective cell, which is the C32 total. From there, we then change from the solver parameters, we then go to the changing variable cells, which are B2 to B31 because they are the odd and even numbers 0 to 30 as each of the city order. Then from there, we go to the evolutionary solver method, which is adding constraints from B2 to B31 as all different, once again, the same cities. This pretty much ensures that the solver only changes cell values when integers 1 to 30 appear only once. So obviously, like we talked about before, we want to hit each city one time, not going to another, and finding the shortest route possible. And obviously, this evolutionary solver method is one that we really not a lot of people have familiarity with. So I just want to give a brief introduction into it. So like we said, like it said in the chapter, it was invented by Michigan professor John Holland. It's a mathematical version of Darwin's survival of the fittest. So pretty much the big thing with it in relation to the problem is that it begins with a population of 100 different tors. And then the value of the objective cell, or C32 in this case, which is the total distance traveled, is selected for each member of the population. Two members of the population are then chosen to breed or pair up together. But the thing with this is they're chosen to breed or pair up together if they have a small total distance. So the smaller the total distance from one city to another, the higher probability that they will breed or pair up. Pretty much keeping in mind that is the objective in mind of the total case itself, is that you want to find the shortest path from one city to another without hitting the same city twice. So we kind of just thought this was a great way to do that and keep the mathematical aspect in mind while also relating it back to the chapter. Thanks for listening to our presentation and looking forward to the comments.